So welcome back. Today we're switching back to quantum bonding theories. We spent some time talking about the classical bonding theory, and I see people smiling. It's not going to be lots of equations. Even if we're talking about quantum bonding theory, I want to make it more of a qualitative fashion. All right. So here are the list of the learning objectives of today. I'll try to finish up everything, but if not, it's also okay. We'll talk about the Morse potential energy. It's a potential energy. It describes how energy changes when you have two hydrogen atoms approaching each other. Then we'll quickly introduce the Born-Oppenheimer approximation, because if you remember when we were talking about multi-electron atoms, it is impossible to solve for the exact Schrodinger equation if you have more than 2 electrons you're interested in. To make our life easier, typically we use the Born-Oppenheimer approximation when we're talking about bonding theories. And then we'll look at something we can solve exact, which is the molecular orbitals of H2+. Remember, 1 electron systems, we can solve it in exact. So H2 is one of those 1 electron molecules. It's hypothetical, but it's 1 electron and we can solve it. And at the end, we'll be talking about how to estimate the shape of your molecular orbitals by using linear combination of atomic orbitals. It's a lot, but we'll go over it one by one. So before we talk about the actual quantum bonding theory, the one question we always want to ask ourselves is, why do we need quantum bonding theory? Why can't we just draw a Lewis-Dot diagram and make those atoms happy with octets of electrons? So here comes to the point that Lewis-Dot diagram or classical bonding theory in general, it works well in most of the scenarios. But when it fails, it will just fail to a point that it doesn't work at all. So oxygen is a typical example. It looks like nice and harmless. We need it to breathe, but its chemical structure is actually pretty complicated. Let's just draw the Lewis-Dot diagram together. All right, we should all be relatively familiar with it. We have oxygen double bonded to another oxygen, and each oxygen has 2 lone pairs. We look at it. We have both oxygen fulfill its octet rule. It doesn't have any formal charge on it. It's a very valid Lewis-Dot diagram. Or the other way to put it is that all electrons are paired in this Lewis-Dot diagram. However, we talked about paramagneticity and dimagneticity when we were talking about electron pairs, right? So if all electrons are paired in your molecule, we're expected to be dimagnetic. But experimentally, you can measure how oxygen molecule behave when you put it in a magnetic field. So what we find out is that experimentally, oxygen, O2 gas, is paramagnetic. And remember, when we're saying some species is paramagnetic, it means it has unpaired electrons. And here we have a clear contradictory between the classical bonding theory, where you can draw the Lewis-Dot diagram, looks like everything paired up, but the reality tells you that oxygen gas has unpaired electrons. I probably may not be able to move very fast to see why O2 has unpaired electrons, but nevertheless, next Wednesday we'll be able to see it. So, quantum bonding theory. First thing first, the Morse potential energy of H2. I'm just gonna very slowly draw stuff on this diagram, but you'll see how I draw them with a detailed walkthrough on the annotated notes. So just pay attention to my drawing and don't worry about copying those things down. What a Morse potential energy diagram is telling you is we're trying to describe what is the energy between these two atoms when they're approaching each other or getting further away? When reading any scientific diagram, the first thing you look at is the x and y axis. It tells you what are the information you should be using in that diagram. On the x-axis, we have the distance. So R stands for distance. So that is the distance between atom HA and HB. So I'm just manually label my hydrogen atom to be A and B. On the y-axis, we have the potential energy between these two atoms, like how these two atoms are filling each other. So let's start from very infinitely apart. We're putting these two atoms infinitely apart from each other, one on the Earth, one on the Moon, if you may. So that's our point A here. So we have our HA and our HB. They're infinitely apart. Maybe I should use a dashed line. Or we see the distance between RAB, between A and B, is approaching infinity. So they don't see each other at all. There's no interaction. Naturally, there's no interaction, so the potential energy between these two atoms are zero, so, or infinitely approaching zero, right? Because we can't really have infinite distance, so this one is infinitely approaching zero. Or VA is infinitely approaching zero. The two atoms don't see each other, they don't interact with each other, there's nothing happening. Taking it to another extreme, when these two atoms are getting very close to each other at point B here. So here, HA and HB, they're getting really, really close to each other. And they're not happy because of the Pauli repulsion theory. Like, you don't want them, they don't want to be close to each other. And also because of the electrostatic repulsion, right? The nuclei are positively charged, they don't want to be close to each other. So here what we have is RAB is approaching zero. And here, our VA, well, VB, that's point B, will approach infinity. And the reason here is because of the nuclear repulsion. So we talk about two extreme cases. Yes?
Is the nuclei still considered a pure particle?
In nature, in reality, the nuclei shouldn't be pure particle. I mean, everything is wave-particle duality. But for this course, when we're talking about difference between electron and nuclei, if we're just focusing on the electronic energy, the nuclei are heavy enough, we can just consider them as particle. But even like my Apple Pencil here is not a pure particle. It has wave property. Anyhow, that's going too far. All right, so here we talk about two different extreme scenarios. One is when the two atoms are super close to each other. It has a very high repulsion energy. And one is when they're super far from each other, they don't interact with each other, so their potential energy approaches zero. They don't see each other, they don't care about each other. What chemists like is at point C. So here is when you have HA and HB, these two atoms, in a good enough position where they're forming a chemical bond, or RAB is roughly equals to RE, where this RE here is defined to be the equilibrium bond length. And in this position, we have our potential energy roughly equals to dE. And that's the minimum energy on your Morse potential surface. All right, so if we draw a line here, that's dE. The real picture is a little bit more complicated than that. So here I want to pause a little bit and let's just think about what is the reality. Right here I'm talking about RAB is roughly equals to your equilibrium bond length. But when we're in the microscopic world, we have the Heisenberg uncertainty principle. So what it means is it is not possible to have your atom in that one single position. Right, there always exists some kind of spread in the position of that particle. So that refers to what we were talking about. Is it a pure particle? Is it a pure nuclei themselves are not even pure particle, and the energy, we cannot have a pure, like, smallest energy on your potential energy surface. Or the other way to put it is we always have some kind of fluctuation around that equilibrium bond length. And that fluctuation is coming from the Heisenberg uncertainty principle. And as a consequence, we have the 0-point energy measured in experimental work, which is called E0. Or D0, if we want to keep my notations correct. All right, so what we're talking about here is the potential at this point C. We can never determine it exactly at point C. So that comes from the Heisenberg uncertainty principle. So delta X times delta P is larger than or equal to H over 4 pi. And in this case, your delta X and delta P can't be 0. All right? So let me just zoom out this part a little bit and spend just one little bit time on it. So when we're talking about the 0-point energy, what we have is this point C here. That's the theoretical equilibrium bond length. That's the theoretical point we're talking about. But experimentally, yes?
What did DE stand for?
What's that? That's just the bond energy at that equilibrium point. So at this point, just since we asked for it, right? So that's the theoretical equilibrium bond energy or potential energy. But in reality, we always exist some fluctuation in your position when you're measuring it. And that fluctuation is called 0-point energy. And as a chemist, one of the properties we want to know is about the bond dissociation energy. So in this case, when we're looking at the bond dissociation energy, again, this is the theoretical bond dissociation energy. That's the theoretical dE. But in QM, we have the 0-point energy E0. So in quantum mechanics, what we can measure experimentally is the difference here, which is my D0. All right, so 3 different things. D0, that's the experimentally measured bond dissociation energy. E naught is the 0-point energy. Coming from the Heisenberg uncertainty principle, delta x, delta p is larger than or equal to h over 4 pi. And then the dE is the theoretical bond dissociation energy. So I'm just going to quickly pause here because in this class we have so many different terms, right? You have so many different energies. Really, really think about it. What is the physical meaning of these terms? For example, in this paper, on this page, one of the example questions would be, hey, I'm giving you the general shape of a Morse potential. Can you just draw the line representing the 0-point energy? Right? Can you draw the line representing the energy dissociation energy, or vice versa? So, just so you know, it's just whenever you're encountering a question, just think about what's the physical meaning behind that terminology. All right. In chemistry, the experimentally measured bond dissociation energy has a different, related definition, and there are different ways to express that energy. It is called bond dissociation energy. Again, we start from a molecule in gas phase, and it is dissociating into its atomic composition, atom A and atom B. So the bond dissociation energy is defined here, right? So my D naught equals to the relative energy here, which is equal to the energy of the product minus the energy of the reactant. So in any chemistry reaction, whenever we're talking about the reaction energy, right, the energy of this transformation, we're always talking about the relative energy between the product and the reactant. So this is the bond dissociation energy. Before we move on, I want to quickly ask you about the same concept. Let's just apply it to an old terminology, the ionization energy. Right? Imagine we have an atom X, and it's being ionized to form a cation and the electron itself. Right, so that's a definition of an ionization energy. So how to write that ionization energy using the same logic here? It's the same idea. You have a chemical transformation from reactant to product. What we're writing is ionization energy equals to energy of the product minus energy of the reactant. But in this case, energy of the product is when these two are infinitely apart. X plus E minus energy of X. So in here, these two are infinitely apart. So then these translates back to our energy diagram. Right, we have the energy diagram of any atom. We have En equals to infinity. They're infinitely apart, so your principal quantum number is approaching infinity. That equals to 0. And E initial. And you can calculate it by doing the difference here. Right. So it's not fancy. There's nothing fancy here. We're just talking about a reaction from reactant to product. What you should be doing is think about what is happening here. how can I use the mathematical expression we learned to represent my initial state and to represent my final state? So here's a summary page. Again, it's available on Cengage, so don't feel the need of actually needs to write everything down. This is the Morse potential we were talking about, right? We start from, say, point A. The two atoms are infinitely apart. They don't feel each other. Your potential energy is approaching zero when the distance is approaching infinity. And imagine when these two atoms are coming closer to each other, it starts to feel some kind of construction interaction, right? So the potential energy is going down. That's an attractive force between the two atoms. It's keep going down until it reaches around that equilibrium bond length at about Re. So here is where your chemical bond formation is taking place. And remember, because we're talking about quantum mechanics, there always exists some kind of zero-point energy due to the Heisenberg uncertainty principle. And as a result, they experimentally measured D naught, or the bond dissociation energy. Will be different from the theoretical minimum on the Morse potential diagram. And if you, 1 second, let me finish it. And if you keep shrinking the distance between the two atoms, eventually you will face the position where the nuclei start to repel each other. Question?
How do you know where to draw your line for
This one, I'm not going to ask you to calculate what the zero-point energy is. So you just need to know there exists a zero-point energy. We can never experimentally measure where that lowest point C is. And you need to know the physical meaning of these lines. All right. So this is a summary of the Morse potential part. Do you have any additional questions before we move on? Yes?
So D naught is the experimentally measured, or the?
Yes, so D naught is the experimentally measurable bond dissociation energy for this H2. You can imagine that's other atoms as well. That already took consideration of the zero-point energy that's here. Okay. And now let's move on to talk about Born-Oppenheimer approximation. So, Born-Oppenheimer approximation, this one I'm just going to quickly touch base on it. It's not a complicated idea. So the need here is we're talking about an approximation that is required for us to solve the Schrodinger equation. Right, remember, here imagine we have a molecule A and B, just random atoms bonded together. And in general, we have the Schrodinger equation, right? The Hamiltonian acting on the wave function gives you the electronic energy times the wave function. And the wave function, by definition, is a probability wave. And when we say it's a probability wave, what we're saying is the wave function squared gives you the probability of finding the electron somewhere in space. So that's a quick review of the Schrodinger equation. Then, before we actually thinking about how to solve it, I mean, we're not going to solve it in class here, but just think about how complicated your problem can be. What is in your Hamiltonian? We went over the Hamiltonian in our Schrodinger equation lecture. So it pretty much has a kinetic term and a potential energy term. Right, the kinetic term is acting more or less like 1/2 mv squared, or in this v in the classical theory, that's more or less a d squared over dx squared. So it's a differential equation. So your Hamiltonian is a differential equation. It contains information about kinetic energy and potential energy of your setup here. So what are the contributors to the Hamiltonian equation in the scenario of our molecule AB? So apparently, we can have the kinetic contribution, just talking about the movement of your nuclei and the electron. So how many things we have? Just imagine we only have one electron on each atom. Then you have the kinetic energy of nuclei A. You have the kinetic energy of nuclei B. And also kinetic energy of some electron 1 surrounding A. And the kinetic energy of some electron surrounding B. Right, so each of these terms is a differential equation. Each of these kinetic terms is a second order differential equation. That's the kinetic part. We haven't talked about the potential part yet, so we already have 4 terms here. The potential part is even more formidable. We're talking about the Coulomb's electrostatic potential, right? Your nuclei is positively charged, your electrons are negatively charged. Whenever you have charged species, they'll have electrostatic interaction. The species with the same charge repel each other. Species with a different sign attracts each other. So that's the Coulomb's law. And if you don't remember, that's my Q1, Q2, 4 pi epsilon r. We see that a long time ago, right? So Q1 and Q2 are the charge of those species, and r is a distance between these charged species. So in the potential term, what we have is your positively charged nuclei is going to repel each other. Your negatively charged electrons are going to repel each other. To make it more complicated, you have 4 pairs of attractive interaction. Right, the nuclei A attracts both electron A and electron B. Nuclei B attracts both electron A and electron B. How many terms we have now? We have a total of 10 terms, and it's just too complicated to be solved, even to get an estimate on what your solution is. So that's why we use the Born-Oppenheimer approximation. So far, we were just talking about why we need the Born-Oppenheimer approximation. And here we're talking about the actual approximation. What it reads is that motions of nuclei and electrons in a molecule can be treated separately. Very straightforward. We're just talking about we're treating the motion separately. And how do we rationalize it? So this is the approximation itself. And then let's rationalize it to give it a little bit more insight. The insight here is that nuclear motions in a molecule is much slower comparing to the velocity of the electrons. Right? Imagine you're standing on, you're in a train that's moving really fast, and you look at outside of the train. What you feel like is outside are pretty much stays, not moving as fast as you are. So the result here is that electrons that are moving faster will see the nuclei as a fixed particle. So A and B around. So electrons are not particles, but if we have the electron somewhere and it's moving around, it will pretty much see your nuclei fixed. So to the point of view of electron, the nuclei are not moving at all. Or the other way to put it is that the electronic wave function, or phi EL, will only depend on the position, not the velocities of the nuclei. All right, so if we're just looking at the electronic wave function, that electronic wave function does not depend on the position of the nuclei. With me so far? Just because electrons are moving fast, they feel the nuclei are not moving at all. So when we're talking about the electronic wave function, we can imagine the velocity of the nuclei to not contribute to my electronic wave function. That's the first piece of rationalization. Second piece of rationalization is when you have nuclei, right? The nuclei is relatively moving slower comparing to the electron. So the consequence here is you have A and B, and the electron to the nuclei almost feels like just some kind of cloud. It's moving so fast, the nuclei can't figure out where that electron is at a given point of time. Or the other way to put it is the nuclei will actually see electron as a delocalized potential, or electron cloud, electron density, if you may. Or the other way around is for the nuclei, it will just view the electron as an electron density. And we can calculate that electron density by using the electronic wave function squared. All right, so a result of the Born-Oppenheimer approximation is that we can simplify the Hamiltonian for a diatomic molecule. So here's a simplified version of it. You don't need to remember it, you just need to know the physical meaning of each term here. So this is the simplified Hamiltonian of the diatomic molecule. And in here, the first term here, T nuclear here, is the kinetic term of the nuclei. So that's just talking about the movement of the nuclei itself. And when the nuclei is moving, it views electron as a delocalized electronic cloud. And then in the middle, that's the nuclei-nuclei repulsion. And at the very end, we have our electronic Hamiltonian. And the electronic Hamiltonian is depending on the position between, the distance between the electron and the nuclei and between the two electrons themselves. So it's a highly simplified version of the Hamiltonian for a molecule. For this course, we're chemists, so we care more about the last term. So from here, we'll be just focusing on that electronic Hamiltonian operator. What we're solving is the electronic wave function. We're solving the electronic energy of molecules. All right? Do we have any questions before we move on? Yes?
Despite the electrons say the nucleus, if it splits, how does it still have kinetic energy?
The electrons still have negative energy, right? So the electrons are not pure particle, yes. But at the same time, it's still charged. So these two are just separate species. It can be charged, but it is not a pure particle. Does that make sense? It's two orthogonal properties of the electron, if you may. All right, so the Born-Oppenheimer approximation here looks complicated, but the take-home message is just we're using the Born-Oppenheimer approximation so we can just focusing on the electronic Hamiltonian, on the electronic energy. We chemists don't worry too much about the movement of the nuclei during a chemical reaction because their movement is relatively slow comparing to the movement of the electron. And for me, for this class, I don't expect you to solve any of these equations, but you do need to know the physical meaning of these equations, like what we did for the Morse potential, right? I don't need you to know the actual position of those points, but you need to know what those points mean. All right, moving on. Now we have a representation. We have our electronic Hamiltonian of the electronic energy. So we will spend some time just solving for the exact molecular orbital for H2+. Remember, whenever we have just one electron system, That's something we can solve exactly. So this is what we have. We're focusing on the electronic Hamiltonian of H2+. What we're solving is the electronic wave function and also consequently solving for the electronic energy of H2+. So using the Born-Oppenheimer approximation, we know the nuclei are fixed. So the Hamiltonian of the electron can be further dissected into this term, first thing. That's my kinetic energy of the electron. All right, this is a differential equation. That's just a Laplacian. That's roughly equals to the second derivative we use for the one-dimensional system. And here, the second term here, by just looking at it, it is a negative term. You should know that it's a attractive forces because that potential energy is negative. So here, that's the electron nuclei attraction potential energy. All right, what we have here is just Q1, Q2 over 4 pi epsilon naught. And at the end, we have our proton-proton repulsion term. And the reason it is proton-proton repulsion is because we're using the bigger R here. We don't have any electron-electron correlation. It's just electron interacting with the fixed nuclei under the Born-Oppenheimer approximation. So that means we human beings can actually solve these one-electron Schrodinger equation exactly. All right. So we will be talking about molecular orbitals from now on. But before we move on, I just want to highlight it again. When we are having exact molecular orbitals, that's equivalent to say that's electronic wave function of your H2+. Like what we did with the atomic orbitals, right? Atomic orbitals are just one electron hydrogenated wave functions. Molecular orbitals are also just electron wave functions, but with H2+. Difference between molecular orbital and atomic orbital, they're both wave functions. Atomic orbital, you have one nuclei. Molecular orbital, you have two nuclei. All right. So molecular orbitals, they are actually just mathematical functions. But these mathematical functions are a bit too complicated for me to actually show you the function. So we'll just look at them qualitatively and get an idea about what they look like. So this is one of the potential energy surface. We see that here. This is our bonding molecular orbital for H2+. We'll see how that closely resembles the shape we just derived for the Morse potential for H2. But this is just calculated actual molecular orbital of H2+. In molecular orbitals, typically you have a pair, whether it's a bonding MO, it has 0 node, or it can also be an anti-bonding MO when there exists 1 node. So let me zoom it out a little bit more for you. Let's just look at this 1 sigma and 1 sigma star. So 1 sigma, that's the lowest energy molecular orbital for H2+. What it means, every term here has some meaning. First term, 1 here. 1, that's my energy index, non-integer. It's more or less equivalent to the principal quantum number in atomic orbitals. Sigma, that tells you this is the cylindrical symmetry. around axis, the bonding axis. So the bonding axis is here. Right, so it's cylindrical around that bonding axis. And we call it a bonding MO. What it means is we have electron densities between the atoms. This one is pretty much the most important take-home message I wish you can get. By just looking at your molecular orbital, if there are electron densities in between the atom, we call it a bonding MO. All right, so what does an anti-bonding MO look like? So an anti-bonding MO, well, we have the same 1, that's for the energy index integer, that's the same. Sigma, that's still cylindrical symmetry around the axis. But in the anti-bonding MO, here we have that star. I'll actually use this pink color. So this star means it is an anti-bonding MO. Or what we're having is the low electron density region between the atoms. And that is equivalent to say there's a node in between the atoms. And how is a node related to the electron density? Remember, node is when your wave function is approaching 0, is at 0, right? So when your phi electron squared equals to 0, that's where your node is. And that's where that low electron density comes from. Yes?
If there were to be multiple atoms, would it be a radial node around it?
So the question is, are we going to talk about multiple atoms? Quick answer is we don't look at more than 2 atoms in the MO theory. We only look at the biatomic molecules. Again, we're talking about just chemical bond, right? What is the nature of one single chemical bond? When you have multiple atoms bonded together, they normally don't bind, say, from like A, and then somehow you have B and C. They don't bind like that normally. It's more or less A binding to B and maybe to a C. So it's important to understand what's the nature of each of these chemical bonds and use them together. And they have very strange behavior when you actually have that 3 system coming in place. Yes?
So how can we use this to define like a double bond? Is it like?
We'll talk about double bond very soon in next one. So we have pi molecular orbitals. Here is, again, I want to pause here and talk about a common misunderstanding. We talk about S, P, and D atomic orbital for hydrogen atom. The idea here is that even if hydrogen atom, the lowest energy configuration is nearly always 1s1, right? The electron is nearly always in that s atomic orbital. But those higher energy atomic orbital exist for your hydrogen atom. It's the same idea. In H2+, nearly always your electron density is in your 1 sigma, in that sigma bonding orbital. But these higher energy pi atomic orbitals still exist for your H2+. So here we have our similar terminology here, right? 1 is my energy index number. And this pi just tells you there exists a node plane that containing the HH axis. So if my axis is highlighted here, that node plane contains that HH axis. You don't need to know what that U means in this case. And what we chemists care more is about bonding or anti-bonding. So when we say there exists a bonding MO, remember that's electron density between atoms. Right, so here is my atom center, that's my nuclei, and we have electron density above and below. So in both cases, even if there exists a node that's containing that axis, this is still a pi bonding molecular orbitals because we have electron density in between the atoms. Likewise, you could imagine what a pi star anti-bonding molecular orbital looks like. So here, we have the anti-bonding molecular orbital. We have one more node. And we have the node between atoms. Right, so this is a node. It's more or less the equivalent to say there's an angular node that defines it is a pi atomic orbital. And this vertical node means there is a low electron density region in between your two hydrogen, and that makes it an anti-bonding. All right? Okay, I don't have enough time to go over to linear combination of atomic orbitals, but I'll pause here for questions if you have. All right, now I'm more than one lecture behind, but it's okay. Let me know if you have any questions, and yes, we'll just talk, because I see people are leaving. And we have multiple deadlines on Sunday, keep that in mind.